So I know your first reaction probably to this page when you see the word spectroscopy, probably groaning inside. You thought you were done with spectroscopy after IR and NMR. I'm just going to introduce very quickly and briefly a new type of spectroscopy. And this one's not going to be as in depth and in as we went into with IR or NMR, but this involves UV visible spectroscopy. The name kind of gives away as far as what portion of the EMR spectrum we're going to use, but we use this a lot to identify conjugated systems because conjugated systems absorb EMR in the UV and visible regions. And here's how this works. Pi electrons can absorb certain wavelengths of EMR to be promoted from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. This is formally called a pi to pi star transition. And the less energy required relates to a higher wavelength of light. So the smaller the gap is between the HOMO and the LUMO, the easier, the less energy is required to promote that electron to a pi star orbital. And the end result is this allows us to compare the conjugation or the lack of in pi systems. So for example, let's compare ethene to 1,3-butadiene. Now, ethene is not a conjugated system. 1,3-butadiene is. So what happens is when it is exposed to EMR, it requires a certain amount of energy to promote that electron up to the LUMO. Now, I want you to note, this is kind of relative, but note the large gap between the HOMO and the LUMO. Now, with 1,3-butadiene, the same phenomenon will happen, but it will do so at a wavelength within the UV region. And that electron will get promoted up to the pi star. And that gap between the HOMO and the LUMO will shrink the more conjugated a system is. So if I have this more conjugation, then the HOMO and the LUMO will be smaller than 1,3-butadiene, and so on and so forth. The more conjugation there is, the less energy will be required. And let's kind of look at some numbers. I do not want you to memorize these. What I want you to look at are the trends. Notice here how these systems are not conjugated dienes. And so they absorb wavelengths of EMR below 200 nanometers, which is where UV starts. Notice as we start to get more conjugated, now this is absorbing light within the UV region, which is like 200 to 400 nanometers. There's one kind of weird guy right here, an isolated diene. Notice how suddenly, even though it is a diene, because it is not conjugated, it kind of shoots right back down into this category of, below 200 nanometers. And notice how when we go from 2 conjugated pi bonds to 3, the number starts to go up. And eventually, if you get enough conjugation, then it goes into the visible region. Like your eyes become spectrometers. So this is what gives a lot of fruits and vegetables their colors. So like a carrot, the reason carrots are orange is because if you look up the structure of beta carotene, I'm not going to put this on the test, but look at beta carotene. I think that's how it's spelled. Beta carotene is kind of like a reddish orange color, and it is highly, highly conjugated. There are a ton of consecutive p orbitals in beta carotene. And so, like, our eyes are basically spectrometers and absorb a certain wavelength of light. And we see that kind of, I don't want to say we see the organic compound, but we see the results of that because the beta carotene is absorbing light in the visible region. So what does a UV spectrum look like? Kind of looks like a big weird hill. And all we really care about is the wavelength max. What's the highest wavelength that is absorbed? And if that is within the UV or visible region, then we know that the system is conjugated. And the higher that number, higher the wavelength, the more conjugated the system. And that's kind of essentially it with UV. That's all we're going to go into that. And so how do we, use this in a problem? So here we have two compounds, two different compounds. I want to emphasize that. They do the same reaction. We'll react them with two equivalents of H2 and palladium to form cyclohexane. So we have compound A, compound B, and reacting with two H2 and palladium, and they get the same result, cyclohexane. Now, what kind of things react with hydrogen and a transition metal catalyst? Alkenes. And if we're using two equivalents, then maybe we're reacting them with a diene. Two double bonds require two equivalents of hydrogen. Each double bond requires one equivalent of hydrogen. So that's why we're using two. Now, how can we tell what the structure is of A and B? Well, if we put both of them in a UV visible spectrometer, notice that A has an absorption around 256. If that's within the 200 to 400 region, what does that tell you about the pi system? This tells you it's a conjugated diene. And B is not within that 200 to 400 region. So this is an unconjugated diene. So let's come up with some structures for A and B. We know it's got to be a six-membered ring, and A has to be conjugated. So I'm just going to put that double, single, double bond pattern. B cannot be conjugated, so the only possibility would be to put them opposite like that. I can't make accumulated diene in a ring because there's way too much strain. So please don't put an answer like this because that doesn't exist. That's an sp hybridized carbon, which wants a 180 degrees bond angle. So you can't use accumulated diene here. It has to be isolated. And that's where we're going to stop with this unit. Please go through the homework. I'll have some extra practice problems as well, and ask questions for things that you need a little bit more clarity on.